All right, I hear the recording in progress, so we'll go ahead and get started. Okay, so we're here, 7.3. I've already done some of 7.3, so I'm a little bit ahead. I'll review some of what we did last time, and we will move on. Okay, quick word about the quiz. So you should have gotten an email back from me about your quiz. If you did not, then let me know right away. And I already sent a solutions video over the weekend also. Okay, but you know how the quizzes work by now. This is our third one. So same deal all the time. I give you the quiz. I give you back a score between 0 and 5. 5 is maximum. And a quick reminder, you get to drop 1 out of every 4 quizzes. Every time we have 4 quizzes, you're allowed to drop 1. So that you know that happens. So we'll have another quiz on Friday, but then the next exam looks like Friday the 24th, right? And you've already seen an exam now. So you pretty much know the way I run the whole semester. Every week there's either a quiz or an exam. And a quick reminder, if I don't get anything from you, if I don't get 4 quiz/exams from you, I might drop you from the course for non-attendance. Okay, by 4, I mean you miss 3 quizzes and 1 test, or 2 quizzes and 2 tests. That's missing too much class, right? So if that happens, even though I say you're not required to join physically, that to me is non-attendance if you do not submit 4 combined quizzes and exams, and I might drop you from the course, right? All right, so that's that about the quiz. Again, if you have any questions about the quiz, let me know, but I've already emailed you all back and sent you the solutions video. And again, if you have any questions, let me know. Okay, so 7.3, we're doing trig substitutions. I'll do review of what happened last time and before moving on, but there's a key page that you want to look at. And you definitely want to put this on your next cheat sheet for trig substitution, page 486. So there's 3 basic types that you have to look at. If you have the square root, it doesn't have to be a square root, but the main idea behind some of these integrals is to get rid of the square root. Either a squared minus x squared, a squared plus x squared, or x squared minus a squared. These are the 3 basic types that they will have. And by the way, in case you're wondering, they turned this around. How come I don't turn this around? Well, we know from before, a squared plus x squared. What about x squared plus a squared? That's the same thing because addition is commutative, right? You can turn around a squared plus x squared and x squared plus a squared are the same thing. But subtraction is not commutative, right? A squared minus x squared is not the same thing as x squared minus a squared. So there's a separate rule for each of those. Okay. And as far as what to put on your cheat sheet, I think you can survive with just this. So I would say put all of this and all of this. Okay. And if you want to put this, you may. So what's all this about? It's to give you a so-called nice angle. You have a nice angle theta so that you don't have to worry about the square roots. You know, negative pi over 2, pi over 2, that's where you want sine to be. And that's where you want tangent to be also. And secant, this looks kind of funny, but it's still a quote unquote nice angle. You want a nice angle in there. And these are the identities. So you've already seen these identities. So it's up to you. Do you want to put that on your cheat sheet or not? I leave that up to you. Okay. So I gave you 1 of each type last time. So I'll show you quickly what happened last time. Okay, so you have to remember your right triangle trigonometry. And again, you're welcome to put this on your formula sheet if you wish also. Draw a generic right triangle, hypotenuse, right? Some angle theta, opposite, hypotenuse, adjacent. And then our SOHCAHTOA from trig, sine of theta is opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. Okay, so number 1, and you only generally look at the thing underneath the square root. You don't worry about, you know, the outside stuff so much. So number 1, 4 minus x squared. So 4 minus x squared, that's the first one, right? A squared minus x squared. So if a squared is 4, that means a is 2. So let x be 2 sine theta. Okay. Then you do your dx. Do your substitution. Now, if you do the substitution correctly, this square root will always clean up. Okay, so in this case, by doing the substitution, that square root ended up being 4 cosine squared, and the square root of 4 cosine squared was 2 cosine. Okay. And then what usually happens is that you do the integration. After you do the integration, you get an expression that only involves theta, but you don't want it to have theta, right? The original problem was an x, so that's where you have to switch the trig. So is there a relationship between theta and x? Yes, it's back here. And that's where you have to do your triangle stuff, your triangulation, I like to call it. Okay, so x is 2 sine theta. That means sine of theta is x over 2. So I drew myself a triangle, opposite over hypotenuse. And you can either do your a squared plus b squared equals c squared to find the missing side, or more often than not, if you just peek back at the original for the funny square root thing, you're going to be correct. So I just peek up here, square root of 4 minus x squared. It's correct, but you normally want to check, is a squared plus b squared equal to c squared? The answer is yes. This thing squared is 4 minus x squared. This thing squared is x squared. Add them up, you get 4, and that's equal to 2 squared. And then you substitute back. Okay, so those are the highlights for number 1. Okay, now number 2. Well, that one had a plus, so there's only one of them that had the plus. That was the middle one, right? X squared plus 4. The middle one, a squared plus x squared. So again, a is 2. So x is a tan theta, means 2 tangent theta. It's on page 486. So that x equals 2 tangent theta. Dx is 2 secant squared theta d theta. You substitute this all in, right? Plug everything in as necessary, right? And again, you get a trig integral. And notice by doing this substitution, the square root cleans up. And that's the whole idea. You want to get rid of the square root stuff. The square root stuff is what you don't want to have. And you do the integral. And blah, 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 blah. Okay, and once again, your final answer has theta, but you can't leave your answer like that. I mean, look at the original, right? Has x. So I can't leave it like that. So I have to change theta. So what relationship is there between theta and x? X is 2 tangent theta. Okay, so I solve for tan theta. Tan theta is x over 2. So tangent is opposite over adjacent. So I make my triangle. Opposite, adjacent. What's the hypotenuse? Well, choice 1, do your a squared plus b squared equals c squared. Choice 2, peek at the original, and you're probably correct. It's not 100% that you're correct, but more than likely it's correct. I'm going to guess it's the square root of x squared plus 4. But it's worth it to double check. Square this, x squared. Square this, 4. Add them up, x squared plus 4. Is that equal to the square of this? Yes, it is. And then you just plug everything in. So I leave the 1/3 alone. I leave the cube alone. But inside secant theta, I have to put this because that is what? Hypotenuse over adjacent. Secant is hypotenuse over adjacent because cosine is adjacent over hypotenuse, right? Secant is the reciprocal of the cosine. So secant is hypotenuse over adjacent. Okay, and then a quick reminder of number 3, x squared minus 4. X squared minus 4 was the third one. X squared minus a squared. So again, a is 2. So x equals 2 secant theta. Dx equals 2 secant theta tangent theta d theta. Plug everything in. So everywhere I see x, I put 2 secant theta. This dx, I put this great big thing here. Work it out. And if you do it the right way, the square root comes out nice. There it is, 4 tangent squared, which comes out to be 2 tangent theta. And then again, blah, 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 work it all out. You have an expression involving theta, 2 tangent theta minus theta, I guess. Okay, but you can't leave it like that. Look at the original, right? X. You can't leave it with theta. So how do I change it? Use this relation. X equals 2 secant theta, which means secant theta is x over 2. I don't like secant. I'm guessing you don't like secant. Think in terms of the reciprocal. Reciprocal of the secant is cosine. So I go cosine theta is 2 over x, right? Then I go from there. And by the way, that means theta is arc cosine, inverse cosine of 2 over x, because I need an expression for theta later. Okay, so I draw my triangle. Cosine is adjacent over hypotenuse. So adjacent is 2, hypotenuse is x. This side, you can do your a squared plus b squared equals c squared, or again, just peek at the original, radical x squared minus 4. I'm just going to put radical x squared minus 4 and double check. Is it true that a squared plus b squared equals c squared? So what is this thing squared? X squared minus 4. What is 2 squared? 4. Add them up, you get x squared. Is that equal to the hypotenuse squared? Yes, it is. And then I just plug everything in. Okay, so there we go with how that went. And I'm going to show you some more. Okay, this one I'm going to call 9 star. It's not our number 9, but it was a number 9 in our previous edition, but it's not the same as our edition. But it's nice to know how to do this type of problem anyway. Okay. And by the way, anytime I do some of these star problems, that means you're also responsible for that kind of problem. It's a good problem. Radical x squared plus 16. Okay. So there's only one of the 3 that has a plus. So once you see a plus, you know it's got to be this one, right? The minus, you got to be careful, right? Is it a squared minus x squared or x squared minus a squared? Does the x squared come first or last? Okay, if there's a plus, there's no question about it. You're going to do this one. So x is equal to a tan theta. There's a 16 here, so a is 4. So x is 4 tangent theta. All right, then what is dx? 4 secant squared theta d theta. So that means right here, I'm going to put 4 secant squared theta d theta. And right here, x, I'm putting 4 tangent theta. So now I have 4 secant squared theta d theta over square root of 4 tan theta squared is 16 tangent squared theta plus 16. Okay, now, if you do these the right way, the square root always cleans up. Let's see if that's true here. Okay, right here, you notice you can factor out the 16, right? So 16 tangent squared theta plus 1. And what is tangent squared theta plus 1? Secant squared theta. Right? You have the identity at 1 plus tangent squared theta is secant squared theta. And take a look at this. Right? What is now the square root of 16 secant squared theta? Well, just 4 secant theta. So 4 secant squared theta d theta over 4 secant theta. Very conveniently, the 4's cancel out. Secant squared divided by secant is secant. So I have the integral of the secant of theta. Okay, and again, you can put this on your cheat sheet. We've talked about that before. But the integral of secant theta d theta is ln absolute value of secant theta plus tangent theta plus c. Okay. And let me see if I can show you again where that one was. So we have a whole list of new antiderivatives. So I'm going to find that for you. Page 483, box 1. Okay. So I talk quickly about the derivation, right? It's a strange derivation, but it works. Multiply top and bottom by secant x plus tangent x because it works. Then you do a u substitution. The derivative of the bottom turns out to be the top. But you can just go straight to this. You can put it on your cheat sheet. Integral of secant ln absolute secant plus tangent plus c. Okay. Right, so the calculus is now done, but you can't leave it like that, right? The original has x. So I do my triangle, right? Triangle trigonometry. X equals 4 tan theta. That means tangent theta is x over 4. So draw my triangle. I always draw my triangles like this. You don't have to. If you like your triangle like that or sideways, that's fine, as long as you have a right angle and pick a theta. Okay, so tangent is opposite over adjacent, x 4. Again, you can either do your a squared plus b squared equals c squared, or just do the trade secret, so to speak. Trade secret. Look back at the original, you're probably right. Square root of x squared plus 16. There it is, square root of x squared plus 16. And we're going to check it. Okay, let's check. A squared plus b squared, x squared plus 4 squared, x squared plus 16. That's exactly what you get when you square this. So you know it works. Again, that's usually the fastest way to do this. It's a little bit faster than doing your a squared plus b squared plus c squared. Okay, secant. And secant is hypotenuse over adjacent. Hypotenuse over adjacent. Plus tangent, x over 4, opposite over adjacent. And common denominator, so right here. I will accept this. This is okay, but if you want the absolute best way to write it, it's actually like this. So I'll have to explain a little bit. So kind of spend a little bit of time. Why can I leave my answer like this? Okay, so what happened to the 4? And how come no bars? So a little bit of a timeout. I could write it like this. ln of a quotient. ln of a quotient is a difference of the logs. So it's ln at the top minus ln at the bottom. ln 4 is a constant. So c minus ln 4 is still c. It will give you all real numbers. Okay, so that's why you can eliminate the minus ln 4. How to go from here to here? Because this thing, believe it or not, is always positive. It's never going to be negative. Okay. Now I have to try to convince you that that's true. Right, so again, c minus ln 4 is still c. C runs through all real numbers. If c runs through all real numbers, c minus ln 4 will also run through all real numbers. So it's okay to just put c. Now, how about this expression? Remember, if you have the bars, it makes everything positive, but I claim this thing is always already positive anyway. So let me see if I can convince you of that. First of all, would you agree if I plug in any positive number, this quantity is definitely positive, right? If I plug in 1, 2, 3, a million, everything here is positive, positive plus positives, square root is positive, add a positive, it's going to be positive, right? So that's no big deal. How about if I plug in 0? 0, 0. Well, 0 here, that's gone. 0 plus 16, 16, square root of 16 is 4. That's positive. Okay. All right, so if I plug in x as a positive number, this is clearly positive. If I plug in 0, it's positive. Okay, now see if I can convince you what happens if I plug in a negative. Okay, so suppose I plug in a negative number. Let me try to ignore the 16 for a moment. Pretend the 16 weren't there. So I just go like that. Suppose I plug in -1. Right there, right there. Okay, -1 squared. What is -1 squared? Well, 1. Square root of 1 is 1, plus a -1, that would be 0. Okay, so that'd be 0. I'm kind of like speculating on this right now. Suppose I plug in -2. -2 squared, 4. Square root of 4, 2, plus a -2, 0. Plug in -10. -10. -10 squared, well, 100. Square root of 100, 10, plus a -10, 0. Okay. I claim that this is equal to 0 for x less than 0. If I plug in any negative quantity, this will be exactly 0. Right? Try one more. -5, -5. -5 squared, 25. Square root of 25 is 5. 5 plus a -5, 0. Okay. So if I just have this quantity for any negative number, this is 0. Now, underneath the square root, I'm adding 16. That's going to make this thing bigger in absolute value. So that will make this whole expression positive now. Right. So all of that to say that this expression is always positive. Therefore, I can drop the bars, and I can drop the 4 because I have this root. Okay. So -ln4 plus c is still plus c. And since radical x squared plus 16 plus x is always positive, I drop the bars there too. Okay, so all of that to say this is the best final answer, but on an exam, I'll let you stop right over there. Okay, I just want to show you that. Okay. All right, so now question 15. And 15 is a definite integral. They're giving you 0 to a. So our final answer, I was going to say it's going to be a real number, but it may involve a, if we pretend a is a real number. Okay, a squared minus x squared. A squared minus x squared. It's the first one, perfectly. A squared minus x squared. So I'm going to go x equals a sine theta. X equals a sine theta. Dx equals a cosine theta d theta. And now I change my limits of integration also, because this is a definite integral. So x equals 0. If I put a 0 here, that means sine of theta is 0. What nice angles like that? 0. So theta is 0. If I plug in x equals a, put an a right there. A equals a sine theta. Well, that means sine of theta has to be 1. Sine of what angle is 1? Pi over 2. So my new integral is from 0 to pi over 2. Okay, right here and right here, I plug in a sine theta. A sine theta, a sine theta. Well, if you square them, you'll get a squared sine squared theta, right? This one and this one. So here we go. A squared sine squared theta, that's x squared. That is the same as that. A squared minus what I just said, a squared minus x squared, a squared minus a squared sine squared theta. Dx. Well, what is dx? The derivative of a sine theta, a cosine theta d theta. So dx becomes my a cosine theta d theta. So here's all the substitutions. That is that from here. That is that. And dx is all this stuff. And take a look at this. You can factor out an a squared. 1 minus sine squared. What's 1 minus sine squared? Cosine squared. Whose square root is a cosine theta. So that's perfect. And that's what we want. So now I have a squared sine squared theta, a cosine theta, another a cosine theta, d theta. So there's no more square root. Okay. That was the whole idea behind this kind of problem. We want to get rid of the square roots. So I would be left with a trig integral, which is why we spent so much time in section 2 on the trig integrals, because we knew that we were show up here. So let's see, I got a squared, a for a grand total of a to the 4th, sine squared, cosine squared. A to the 4th, sine squared, cosine squared. Okay, this was the harder case scenario from the previous section where we said we didn't like it if we have only even exponents, right? From the previous section, it was better if we had at least one odd exponent. Okay, so one odd and one even, or both odd, that was the nice case. The harder case was if you have only even exponents. So if you have only even exponents, I have to use the identity, right? And put the identities on your cheat sheet. What is sine squared of theta from trig? 1 minus cosine 2 theta over 2. And what is cosine squared theta? 1 plus cosine 2 theta over 2. So this problem is nice in that it reviews all of these rules that we had from before. So put these on your formula sheet. All right, now I got a minus b, a plus b, which is a squared minus b squared. Okay. Well, 2 times 2 is 4. Take it outside. A to the 4th over 4. And that times that, being a minus b, a plus b, is a squared minus b squared. So I have 1 minus cosine squared 2 theta. Okay. But what is 1 minus cosine squared of something? Sine squared of 2 theta. A to the 4th over 4, integral from 0 to pi over 2, sine squared 2 theta. So now I'm integrating sine squared of some angle, the angle being 2 theta. Remember, 2 theta is just an angle. If theta is an angle, double it, still an angle, right? So don't get thrown off by the 2 theta business. You know, if 15 degrees, that's an angle, double it, 30 degrees, still an angle, right? Or pi over 3, that's an angle, double it, 2 pi over 3, that's still an angle. So it obeys all the properties of angles. So this is sine squared of an angle with an even exponent. So I do the same trick as before. I use this identity once more. Where'd it go? Right? Sine squared of an angle is 1 minus cosine double the angle over 2. Right? So here we go. Sine squared 2 theta. 1 minus cosine double the angle over 2. So what is double of 2 theta? 4 theta. Okay, so that was a little bit more tricky. Okay, 4 times 2 is 8. I bring that outside. Now I'm finally ready to integrate this. So integral of 1 d theta is theta. Integral of negative cosine 4 theta is negative sine 4 theta times 1/4. Again, chain rule in reverse. If I were differentiating and I got to this stage, I would multiply by 4. Since I'm integrating, I would multiply by 1/4. Again, as a double check, take the derivative of this. What's the derivative of this, right? Derivative of theta is 1. Derivative of negative 1/4 sine of 4 theta is negative 1/4 cosine 4 theta times 4. That 4 knocks out the 1/4, and you get that back. Okay, plug in 0, you get 0. 0 minus sine of 0 is 0. Pi over 2. So pi over 2 goes here. If you plug in pi over 2 here, you're taking the sine of 2 pi. Sine of 2 pi is the same as the sine of 0, which is 0. That happens a lot when you do these substitutions, that this disappears because of 0, that disappears. Quite often, even this one disappears. So the only thing of substance is this part right over here. So final answer is pi a to the 4th over 16. Okay. Right, so that's the way that one goes. Yeah, I will set you up with 21, but I wasn't going to do it in its entirety, just get you the setup for it. X squared over radical 9 minus 25 x squared. I'm not sure if I even showed you all the problems. I'll give that to you again. Let's see, what do you have to do? Up to 29. Okay, I don't remember if I showed you the problem, so if I did, that's okay, I'll show you again. Page 491. So for those of you who don't have the book and aren't getting it, that doesn't seem to want to focus on them right now. Yeah, okay. I'm going to change something also. I've decided to skip problem 19. Let me put that right. It comes out to be really long. Skip 19, 7.3. Okay. Okay, I was going to show you a setup for 21, but yeah, I'll talk first about 17. So yeah, I'm not going to do 17, but I'll just talk about it. 17 kind of fits the category of don't forget all the integration rules that we had before. First of all, notice there's a 7. You might get thrown up by the 7. What number squared is 7? Square root of 7. Okay. But I'm not going to do the problem that way. You could, but it's a lot messier. Kind of take a step back at 17. Look at what you got. X squared minus 7, x. What's the derivative of x squared minus 7? 2x. So 17 is kind of like, hey, don't forget all the integration that you had before. I would not do 17 by all this stuff. Just do a u substitution. I'll just tell you u equals x squared minus 7, etc. That is a lot faster. So just do 17 by a regular u substitution. Now, if the numerator had been x squared over radical x squared minus 7, then I'm stuck. I have no choice but to do it by what I suggested. Okay. But for something like this, just do your regular u substitution. Right? U equals x squared minus 7, du equals what? 2x dx, and so on. Okay. Okay, set you up with 21. Let me show you these once more. You will notice for these three, page 486, there's no coefficient in front of x squared. It's just x squared. It isn't saying 9x squared or 25x squared or whatever. Right? For these, no coefficient in front of the x squared, except for 1. You would say it's 1. But look at 21. There's a 25 here. So what do I do when there's a 25 there? I need to have this have only x squared. I'll divide top and bottom by radical 25, as it were, which is fine. Okay. So watch what I did here. This is the original, right? X squared over radical 9 minus 25x squared dx. See, I need to get this to be just x squared. Those three roots that I had were just x squared, not 25x squared. So I'll divide by 25 underneath the radical, which is the same as dividing by 5 outside the radical. So these two, I've divided top and bottom by 5. So I get an equivalent expression. That's what I'm saying. Okay. Or you can say divide by 5, divide by 5, and divided by 5 is of the form dividing by 25 underneath the radical. Okay, then this divided by 5, I bring that outside 1/5. Okay, 9 over 25 minus x squared. Okay, so now it's the way that I like it. It now looks like a squared minus x squared. See, for 21, you had to force the integral to look the way that you wanted it. And you needed to make it look like a table. See, I just want x squared. I don't want 25x squared or whatever. Okay, now it looks like a squared minus x squared, the first one. And what number squared is 9 over 25? 3/5. Okay, so x equals 3/5 sine theta, and then I'll just say et cetera from there. That means you finish the rest of that. Okay, so that's a setup for that one. And then 23, it involves completing the square. It's a little bit clumsy. Dx over square root of x squared plus 2x plus 5. Okay, that looks like a mean trick. But there's a way to get around it. Let's see. Well, I'm noticing what I have isn't the same either. I got to do a star. Sorry, 23 star. Actually, my 23 star is harder than 23. So I'll address 23. It works in a similar fashion to my 23 star. But they actually made it easier. So x squared plus 2x plus 5. If I have time, I'll come back to it. But this is actually much harder. So what do I do with this? Okay, so write it like this: negative x squared plus 4x plus 5. That's certainly the same thing, right? And then we have to do a variation of completing the square. Okay, so completing the square again. So here's what you do. Separate out the 5. Keep the 5 out of it. Take out the negative parentheses x squared minus 4x. Okay, so if I cover these up, okay, I don't have a third handout. Distribute all this. Negative x squared plus 4x plus 5. So that's the same as the original. Agreed? I factored out a -1 from these two guys here. Factor out a -1. I have negative parentheses x squared minus 4x, then plus 5. Then I complete the square, half and square, that you've done many times before in your algebra and pre-calc probably. Okay, so half of -4 is -2. Square it, 4. So in red, I put +4, but that +4 is really -4. It's distributed by a negative, so I need another +4 here. So these two combine to be 0. -4 plus 4. So I claim this whole thing is equivalent to the original. And you can double check, see if this is equivalent to the original. Negative x squared, there it is, minus a -4x plus 4x, plus 5, there it is. So what did I introduce new? A -4 and then a plus 4. So it is equivalent. Okay, so the whole idea is now I can factor this into x minus 2 squared. I got the negative of x minus 2 squared plus 9, which I can turn around and say is radical 9 minus x minus 2 squared dx. Then I'll do a t substitution. Okay. I don't want to do a u substitution because I want to save u for later, just in case. So I said that t equal x minus 2, dt is dx. So my new integral is radical 9 minus t squared dt, and now it's the way that I want it to be. Except instead of x, it's t, but that's okay. 9 minus t squared. 9 minus t squared. That's the first one. 9 minus x squared. 9 minus t squared. So from here, t equals 3 sine theta, dt equals 3 cosine theta, d theta, and then etc. You continue on with that one. Okay, that was 23 star. Your actual 23 is easier. I'll give you the heads up on that one. X squared plus 2x plus 5. So the game I'm playing here is almost like this. It's saying, I wish this were a 1. X squared plus 2x plus 1. So why would I want it to be a 1? Because x squared plus 2x plus 1 is x plus 1 quantity squared. But it's a 5. That's actually not going to be that bad, because I can write it as x squared plus 2x plus 1, and then plus 4. Okay, so let me give you a quick setup on that. I think I got time. So the actual 23, dx over radical x squared plus 2x plus 5. Treat it like so. X squared plus 2x plus 1 plus 4. And now, this is x plus 1 squared. Then switch over to a different letter, like t. Call it t. T equals x plus 1. dt equals dx. So dx is the same as dt. X plus 1 is now t. T squared plus 4. And there we go. T squared plus a squared. Well, that was the middle one, right? That's the only one that had a plus. So the second one down. So x is a tan theta. What's a? 2, because that's t squared plus 2 squared, right? So t equals 2 tan theta. dt is 2 secant squared theta d theta. And then I'll just say etc. Okay. All right, see, we're just about out of time. I'll just mention one more thing. I'll continue tomorrow. But be quiet after a moment. You sort of do that same trick for 27. Oh yeah, for 20, you have to do 25. Let's see. Yeah, we had to do 25. 25, a good way to do 25 is to look at what I did for 23 star. It's very similar. Okay. So I'll just say like 23 star. 27, I'll go ahead and give you the hint. It's almost the same hint as over here. It's like you say, I wish there was a +1. Put it, and then just subtract it. Okay, so this one you would go square root of x squared plus 2x plus 1 minus 1, which is square root of x plus 1 squared minus 1. Okay, so that's how you do that square root part right over there. Okay, so I say, oh, if I had a +1, I'd make it a perfect square. So I just add 1, quickly subtract 1, turn it into x plus 1 squared, and do my t substitution. Okay, so again, you would do t equals x plus 1, etc. after that. Okay. All right, so we're just about out of time, so I'll stop. Pretty much done with this section. Again, skip problem 19. We have one more problem, 29. So I'll show you 29 tomorrow, I believe. And then I can get started with some of 7.4, which is on partial fractions. Okay. All right, so I think that's it. Let me stop the share. Anybody have a quick question that you want to ask me right now? Otherwise, we'll quit. All right, folks, that'll do it for today. All right, so we'll see you all next time. And have a good day, everybody. Okay, bye. Yeah.